Hi, everyone. Welcome to the last unit of Chem 28, the first semester of organic chemistry. Yeah, it's time to wrap things up. We're going to split this last key concepts into two videos. So we'll do half of it now and half later. Okay, we're in unit 5. No parts. This is it. It's a shorter unit right before the final exam. And hopefully we're doing this ahead of time to give yourselves plenty of time to see the new material and then still be able to settle into it and review for the final. Okay, unit 5, we're going to talk about conjugated compounds. And it's another aspect of the alkenes we saw before, but not just alkenes. It can be any pi bond or a couple of pi bonds. So conjugated compounds, there's the pen, simply means, well, one simple way is that you have alternating double and single bonds. Now, I should be clear, this is the most common way you can get conjugation, is where you alternate a double with a single bond. But that's not the only way. It just happens to be the most common. And when this happens, you get a double bond, and then a single bond, double bond, then a single bond, double bond, and so on. Now you have a conjugated pi system. And what happens is these pi electrons are actually free to roam. So as I drew this out with 7 carbon atoms in my molecule, 6 of them are involved in double bonds. Well, it turns out these 2 pi electrons that make up the pi bond, they're free to roam across all 6 carbons. We say they're not localized, pinned down between 2 carbons. They're spread out, so they are delocalized. I know, there's the word. So we talk about delocalized electrons. And the main point, the main feature, is that if the electrons are free to roam across more atoms, they're more spread out. And if they're not pinned down, it makes it harder for reagents to react with them. By spreading out the electrons, the molecule becomes more stable, more resistant to reactions. And stability and reactivity are opposites, right? Something that's more reactive is less stable. Something that's more stable, less reactive. Okay, spreading out the electrons make them more stable, less reactive. Okay, let's look at one of the simpler cases and just clarify what we're talking about. We got an alkene here, and then a single bond, and another alkene. So it's alternating double, single, double. Alternating double and single bonds, that's one way of seeing that the system is conjugated. These pi bonds are kind of connected together. This one breaks the pattern. It is not conjugated or non-conjugated, right? You got a pi bond here, another one here, and then we have a pair of single bonds that separate the 2 pi bonds. More importantly, there's a carbon in between that does not contain a pi bond, or more to the point, it's not sp2, right? So these carbons are sp2, 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 but the carbon in between the 2 pi systems is sp3. That's the main reason why it's not conjugated. Okay, well now I hope you can identify the pattern, double, single, double, not too bad. What's really going on? Well, let's go back to general chemistry when we discussed the pi bonds, the double bonds back then. We said that the pi bond involves 2 p orbitals sideways overlapping to create a bonding orbital and an antibonding orbital. Remember the pi bond or the pi orbital and the pi star antibonding orbital? And they look like this. And what we're saying here is that when the p orbitals sideways overlap to make a bonding orbital, these 2 lobes just define a volume of space, a parking lot, a flight pattern, whatever you want to call it. It's a region above and below. So this region is below the molecule. And the 2 electrons that go into the pi bond are free to go anywhere in this volume of space. That's what we mean by a pi bond. 2 electrons in this red one or this blue one down below, flying all about in their flight patterns. So a conjugated system, same idea, but now you have 4 of them in a row, right? So, whoops. So we got a carbon nucleus here, and then a double bond to another carbon, a single bond to a carbon. This carbon's right here. And then we have a double bond the fourth carbon. And so when you focus on this pi bond, we think about these two p orbitals sideways overlapping. And when you think about this pi bond, I think about these two p orbitals sideways overlapping. But if these two can overlap and these two overlap, why not these two? And it's true. Nature says they can. Why not? They're set up the same way. The one difference you might note is that a single bond is longer, weaker than a double bond, which is shorter and stronger. So the distance between these two carbons actually could be a little bit longer because it's a single bond. But those volumes still could overlap. And so if you look at the molecular orbitals, take these atomic orbitals, the p orbitals, and mix them, 4 orbitals in, 4 orbitals out. We get these 4 molecular orbitals. 2 of them are bonding, and 2 of them are antibonding. Okay, the lowest one is really showing us how the electrons are delocalized. So you mix these p orbitals and you get this first orbital, which is everybody on top is overlapping and everyone on the bottom is overlapping. And you can fill this one orbital with 2 electrons and they can go anywhere. Those 2 electrons are free to roam anywhere above those 4 carbons and anywhere below. So one could be over here, another one could be up here, and just anywhere. And so if you have a reagent that's looking to attack a pi bond, it's looking to grab 2 electrons with 1 collision, right? So what's a chemical reaction on the molecular level? 2 reagents colliding, and hopefully you have a transfer of atoms or some other reaction taking place at the collision. And if your 2 electrons aren't at the point of collision, no reaction with the pi bond. And so that makes this conjugated system, that's what it is, double bond, single, double bond, so much more stable. The 2 electrons are free to roam anywhere in there. So maybe you pick out these 2 electrons of this first pi bond and say, okay, you 2 electrons, you're free to go anywhere about these carbons. The other 2 pi electrons, you go into the next higher up orbital. But guess what? It looks like the first one, except there's a nodal plane, a region where you can't go. So there's a little area, little volume, I should say, it's 3-dimensional, where electrons can't go. But the electrons can hang out up in here, over in here, over in here, over there. Again, these 2 electrons in the second pi bond are free to go anywhere. They just can't hang out in between. And they're okay with that. Sometimes it'll be up here, over there, over there, over there. And you might be saying, well, wait, how does this electron get across there if it can never be in between? Well, electrons can behave like waves. And as a wave, it can kind of tunnel through, quantum tunneling. Anyways, this is the theory. Electrons can behave as waves, and it can tunnel through from one region to the other. Bottom line is experimental data shows that all 4 electrons are free to roam above all 4 carbons. They're not localized like a regular pi bond would be, where these 2 electrons in a non-conjugated alkene, those 2 electrons are forced to be above and below these 2 carbons. But if it's conjugated, 2 electrons can be anywhere among the 4 carbons. Delocalized, much more stable. Yep, that's bottom line. It's free to roam. Because pi electrons are spread out, they're harder for reagents to find to react with. That makes them more stable than isolated. So just to settle the score here, isolated are the normal alkenes, somewhat reactive. I'm thinking of chapter of unit 2 and all those alkene reactions, right? You can make epoxides out of these. You can react with HBr. You can add Br2, you can add ozone, and hydrogen gas and palladium. All right, there's a lot of reactions with alkenes because they're reactive. But if you conjugate them, that makes them a little more stable. They can still do those reactions, but they're slower. Sometimes you have to heat them up to make them go. And then we got this case, which is very unstable. The accumulated, where it's not alternating double, single, double, or just a double bond isolated from another double bond. This is where you pack them side by side, and this middle carbon must be sp hybridized. And it turns out that makes us very reactive. The electrons are very much localized. This is called an alkene. If you go back into unit 1, I think, when we talked about sp, sp2, sp3 orbitals, we talked about alkenes being very reactive. So avoid this, nature does. So try not to have accumulated alkenes in your structures because they're very unlikely. Nature doesn't like these. She likes the more stable ones. So this is the most stable. And this would be, I don't know, somewhat in another adjective. Cool. And it's not isolated to the pi bonds of alkenes, ketone, aldehyde, ester, whatever. That's a pi bond, single bond, pi bond, double, single, double. This is conjugated. And then we talked about one of nature's favorite functional groups, the benzene ring. Yep, same deal. One of the reasons, and we'll learn more about it next semester when we talk about aromatic compounds, which benzene is one of the aromatic compounds. It is in fact conjugated. It's double, single, double, single, double, single, completely conjugated throughout. And now well, there's 3 pi bonds, so there's 6 pi electrons. They're free to go anywhere above and below the ring. Makes them quite stable and difficult to react with. Cool. Okay, that's conjugation. Ooh. All right, so what are some outcomes of conjugation? Well, one, that makes alkenes more stable if they're conjugated. And 2, you can actually get some unusual products because of conjugation. So take another peek at Key Concepts, Unit 5. Here's one of the outcomes of conjugation. It affects some reactions we've already studied. So if we go back to Unit 2, we know about adding HCl, HBr, and HI, Cl2 and Br2 to alkenes. Well, you can still do that. And what we start to see are some unexpected products. So first do the normal case. So look at this conjugated diene, paired double bonds, add HBr, and then look at the product here. And it looks like this alkene reacted. So maybe we added one equivalent. One equivalent HBr, and whoever put this together decided, okay, this is the pi bond that's going to react, and it's a 50-50 shot. So they picked this side. And what's HBr do? It adds by Markovnikov addition, right? So the hydrogen goes to the carbon of the alkene with more hydrogens. This carbon has 2 H's, the other carbon only has 1. So this hydrogen goes to the carbon at the end of the chain. There it is. We get a carbocation here, and the Br minus attacks it, adds to the other carbon, and we have our normal product that we saw in Unit 2. We also get this product where the hydrogen and the bromine are on either ends of where the original alkenes were. If you want to number this, maybe you'd start by numbering it from this end when you're naming it, 1, 2, 3, 4. So the first case is where we have the normal case, Markovnikov addition, and HBr added to the atoms, carbon 1 and carbon 2. Carbon 1 and carbon 2 got the H in the Br. So we call that 1,2 addition. Somewhere else in my notes, we got 1,2 adduct. You don't have to know that, but if you see it, you know what they're talking about. They're talking about the addition product. Chemists making up words. Whoops. So we got the addition product. So take the add and the uct. You get adduct, addition product. Yeah, clever, I guess. but also at the same time, you not only get the normal 1,2 addition product, you get the 1,4. On carbons 1 and 4 went the hydrogen and the bromine. You get both of these. You're going to have to list both on the exam. Later in this video, we'll talk about, well, which one's the major product? It depends on temperature. We'll talk about that in a little bit. For now, for Unit 5, the nitty-gritty is you need to be able to draw these 2 products whenever you use one of these 4 reactants. So I'm gonna limit myself to choosing only those 4 reactants with conjugated dienes. Now, do we have to review that? This is a pair of alkenes. There's 2 alkenes. I'm not spelling alkenes correctly. And remember, if you had 2 methyls, it would be dimethyl. If you had 2 chloros, it would be dichloro. Well, we have 2 enes, so it's diene. Yep. And then what's special about them? It's alternating double, single, double. They're conjugated dienes. Let's look at the mechanism to explain the 1,4 product. Okay, well, it's not a new mechanism. It's just a new application of an old mechanism. Let me draw it the same way it appears there. Just keep things consistent, but you don't have to. Okay, so again, we're going to react with 1 equivalent. If you happen to add a second equivalent, more HBr, then the second double bond will react to. Okay, we're just going to look at the first case, 1 equivalent. And then we chose the closest pi bond is the one that's going to react. And that's a mechanistic step we saw before. The pi electrons grab the H+, and bromine's cool with that because it's more electronegative than hydrogen, so it's going to pull on these bonding electrons and make it a new lone pair. And the first step, the rich gets richer, so the hydrogen goes to the carbon with more hydrogens. The other pi bond didn't react, so it's over there still. And then this poor carbon is missing a bond. So it's now a carbocation. What degree is that carbocation? Primary, secondary, tertiary, or well, it's not going to be quaternary. Can't be a carbocation if it's making 4 bonds. Can't be quaternary. That's secondary. Remember you talked to the carbon. Hey, carbon, how many carbon atoms are you attached to? And this carbon says, oh, I got a carbon on my left and 1 on my right. 2, I'm secondary. And so sometimes the bromide anion that was just formed can attack that and add to that secondary carbon and make the 1,2 product, right? So if we call this carbons 1 and 2, then the H and Br went to carbons 1 and 2. That's your 1,2 product, or 1,2 addition, or 1,2 adduct. Lots of choices. One more thing about that secondary carbocation. I'm sure some of you picked up on it. It's next door to a double bond. It is also allylic. It's allylic, an allylic carbocation. Why is that important? It's because it's resonance stabilized. So we should draw a resonance structure, and that's using this double-headed arrow, not an equilibrium arrow, but double-headed arrow. And it says, hey, sometimes the pi bond rolls over so that this carbon that's missing a bond will then share these pi electrons. And unfortunately, the carbon at the end of the chain now is missing a bond, so now it's positive. What degree is this carbocation? Primary. It's a primary carbocation. Will you allow me to abbreviate carbocation CC+? There you go. So which is more stable, the primary or the secondary? Secondary carbocation is more stable, but these are both fairly stable because they're both resonance stabilized. It's an allylic carbocation. So sure, they're both pretty stabilized. The secondary one's a little more stable. But anyways, sometimes the bromide ion attacks this form. Let's go this way. So the bromine will add to this carbon at the end of the chain. And the double bond ends up in the middle. Because of resonance, the pi bond moved. And then we're attaching hydrogen on carbon 1 and the bromine on carbon 4. This is your 1,4 product. What isomer, which isomer do we have here? Is that an E to Z isomer? Is that a cis or a trans? This is actually trans. So you actually do get the cis product as well. Okay, so I will very likely be lenient on the exam if you forget that one, but you get both of these. I'll probably be prone to give you full credit, but just be aware that if you make trans, you can also make the cis isomer as well. So maybe that's one way of drawing it. The cis 1,4 product. Between the cis and the trans, these two, which one's more stable? Trans, it's got more room. Between the 1,2 product and the 1,4 product, which one's more stable? Zaitseau's rule, remember Zaitseau's rule? The most substituted alkene is your major product. Let's get a different color here. If you circle the alkene, you cut through 2 bonds. This is di-substituted. Just abbreviate that di-sub. And this is mono-substituted. There's fewer groups on this alkene. So the di-substituted products will outnumber the mono-substituted normally. This is the more stable product. I would predict this is the major product. However, the secondary carbocation is more stable than primary, so you might think, wait, if this is more stable, shouldn't that happen more often and make the mono-substituted alkene? Okay, that's a question we'll answer in just a minute. But for now, just take in the steps of the mechanism. Hopefully you recognize them from unit 2. Pi bond grabs an H+, bromine leaves as Br-, and you create a carbocation. And now because you had a conjugated alkene, you will get resonance stabilization. And you need to draw both resonance structures. Sadly, there may be more than one resonance structures in some cases. You'll need to draw them all. And then for every carbocation, the bromide, Br-, can add to that carbocation, the carbon with the positive charge, and complete a product. Cool. Okay, so that's the mechanism for this conjugate addition. You can call it conjugate addition. We call it electrophilic addition to alkenes back in Key Concepts Unit 2. So we can just use the same name, electrophilic addition to conjugated dienes. Nice. Oh, okay, we knocked that down. Let's talk about product distribution, or what's our major product? Well, I kind of said the temperature plays a role. So let's talk about that a little bit more. Okay, this topic, second one for this video, is kinetic versus thermodynamic control. Okay, so back in general chemistry, you talked about kinetics. That's where you measured the rates of reaction, how fast the reaction goes. You also looked at free energy, delta H, the heat of reaction, and you looked at thermodynamics and entropy changes and things like that. And there you're talking about energy and, well, in this context, stability, the most stable compounds. And so we have an interplay between these two. We hinted at that when we looked at the mechanism. We said, hey, there's a couple things going on. The secondary carbocation is more stable than primary. So shouldn't it be easier to make secondary? It's more stable. Isn't it faster to make the secondary? So there's a kinetic feature here in the first step. But we also said, hey, Zaitseau's rule says that di-substituted alkene is more stable than the mono-substituted, or thermodynamically, the di-substituted alkene is more stable. So kinetically, we're favoring the secondary carbocation faster to be made, but thermodynamically, we favor the di-substituted, the 1,4 product, because it gives us the most substituted alkene, more stable. Okay, so that's actually what we mean by kinetic versus thermodynamic control. Okay, and so you can actually control your product distribution. You can choose which product you want, the 1,2 product or the 1,4, using temperature. And here's how it plays out. You get kinetic control at low temperatures. So lower the reaction temperature, and I don't know how low it takes. It depends on each reaction. Sometimes ice temperature works. You might need dry ice temperature. You might need liquid nitrogen temperature, or maybe at room temperature that's low enough. It depends on the reaction. But at some lower temperature, the faster reaction is going to occur more often and make the most product. You need a low temperature so that you don't get an equilibrium forming between the products and the reactants. Kinetic control just depends on just a low enough temperature so it can go over the activation energy hill in your energy diagram. It can just have enough energy to make the product, but don't go backwards and set up equilibrium. No, just make as much of the fastest product as you can. And it turns out for this reaction, electrophilic addition of conjugated dienes, the 1,2 product is your kinetic product. That's the one that goes through a secondary carbocation. But if you increase the temperature, now you get thermodynamic control. At higher temperatures, the fast reaction still happens because it's faster rate, but the higher temperature allows the reaction to go backwards and reform the starting material. And then it can go forward again and go backward again. It sets up equilibrium, and now thermodynamics takes control. Nature's going to prefer to make the more stable product. So as it goes from reactants to products, there's 2 products, the 1,2 product and the 1,4. It'll start forming more of the more stable product. And the less stable one, the 1,2, will be more often the one that reverses and has a higher chance of becoming the 1,4. So now the reaction can start again once it reverses, and it continue to go forward and reverse, setting up the equilibrium. And you add equilibrium, the more stable product now is in highest concentration. If you didn't catch all that, you could rewind it, but stay with me. We'll look at it again in a little more detail. Here's the specific case. We'll look at 1,3-butadiene reacting with 1 equivalent of HBr, and at ice water temperature, you get 71% of the 1,2 product, the kinetic product. We're at low temperatures, or at least 40, 0 degrees is lower than 40, 71 degrees. But if you warm it up just beyond body temperature is about 37 degrees Celsius. So hold it in your hand, take it out of the ice water, let the reaction go now at, higher than room temperature, body temperature, a little bit higher. Now you don't get the major product being the kinetic product. Now it's over here. It's a 1,4 addict. That's your thermodynamic product. The more stable product, the dye-substituted product. Cool. Okay, so that's the outcome. So now you choose for this reaction, which one do you want? You want 71% of this one? Well, let the reaction go at 0 degrees Celsius. No, maybe I want the other one, the 1,4 product. Well, then warm it up to 40 degrees. Let it reach equilibrium, and you'll have 85% of this. What's really going on? We need an energy diagram to see the whole scenario. Okay, so start with 1,3-butadiene, add 1 equivalent of HBr, one of the pi bonds. I guess we're picking this one again. This pi bond's going to grab the H and make a carbocation that's secondary. And then sometimes it can make, through resonance, I won't move the atoms. Remember, when you draw resonance structures, you can only move electrons. You cannot move the atoms. So I got H2C, H2C, CH, CH, CH3, although I need more room to show the pi bond. So I'm not going to move them. I'm just going to stretch them out a little bit. There we go. So sometimes the pi bond's at the end, and you get a secondary carbocation, but the pi bond can shift over to here. And now this one is your carbocation, that's primary. And so the primary carbocation is more unstable than secondary, so it has a higher activation energy. Actually, it should have a higher, the intermediate should be a little higher in energy. To go over this activation energy requires the less stable carbocation. That's why it's higher in energy. This one is lower in energy. Well, it's secondary. It's easier to get over this hill. So it's easier to go over this small hill at low temperatures and make the kinetic product. This one. And it's not as low in energy because this one's more stable. It's lower here. But at low temperatures, there's not enough energy to go backwards. Look at this huge activation energy if you have to go backwards. going forwards, you need this much energy and then go down this hill and go down to here. And then if cold temperatures, you don't have enough energy, they go backwards. But now warm it up. And now you can make this go over this hill really fast, make some products. But now at higher temperatures, you can go backwards and reform the carbocation, which then can isomerize. It can form the resin structure. And then sometimes this can react with bromine to make 1,4 product, which is more stable, lower in energy, more stable. And now that actually has a higher activation energy than this one. So as you make a mixture of products, sometimes you go over to the small hill, sometimes you go over to the high, larger hill. You make these two molecules at high temperatures. A lot of this material can go backwards, go here and try again. And then when it makes this more stable one, that activation energy is much higher, less likely. Doesn't happen as often. Stays down here, the more stable product. This one reverses. Sometimes it goes over here and back and forth it goes, sets up equilibrium so that at high temperatures, you get more of the 1,4 product. Cool. Summarize that up. Low temperatures, kinetic control. Fast reaction gives you a major product. High temperatures, thermodynamic. That's where the more stable product is a major product. Cool. And we'll stop this video right here and continue Unit 5 in the next video. Have a good one.